So we are back to our knapsack problem, right? So we looked at this knapsack problem in greedy algorithms, right? And so the particular variant that we looked at was called fractional knapsack, right? So fractional knapsack means you can take any fraction of the quantities that are available, and when you do that, then you can develop a greedy algorithm which works very fast. But if you have the other variant, which is 0-1 knapsack, or generalization, where you have you take one or more instances of each item, then the problem actually is quite difficult to solve. It's actually an NP complete problem. But if you pretend for a minute that we don't need linear in the size of the input, but only linear in the size of in the total weight, okay, or polynomial in total weight, then you can have an algorithm which says O of n w, right? So notice that w is not input size, right? It's a value, right? So it's the sum of the weights of all the quantities, and you obviously need only log w bits to capture w, which means that you should. So this means that this is an algorithm which, instead of being linear in log w, it's actually exponential in log w, right? So that's why this is not an efficient algorithm. Nevertheless, there are situations where you might want to use this, and you might be interested in an optimal solution. So let's look at how one goes about solving the problem. Okay, so what we want to do is we want to compute k of w, which is the optimal value you can get given a budget of w, right? So you have a budget of w, and you want to find out what is the maximum value you can get, right? And the maximum value for a weight of w will depend upon maximum value I can get for w prime, where w prime is smaller than w. Okay? So that is a dependency, right? So k of w will depend upon k of w prime for all w prime that's less than w. Okay? So which w prime to consider? Well, you can think about it this way. You can say, if I'm trying to decide whether I want to include item I or not. Okay? And notice that this is a knapsack with repetition, so you don't have to worry about whether you already picked I or not. Okay? You might have picked I before, you can pick it again. Okay? So, but then if the ith item has a weight of wi, then you can, you have to spend at least wi of your budget, which means that if you pick the ith item this time, then you can get your best value by picking, by ensuring that the rest of the items that you pick correspond to the best valuation for w minus wi, right? So you're trying to pick the ith item. Ith item has weight, a weight of lowercase wi, and so if you maximize the value that you can get for w minus wi, and then add wi, then add the ith item, then you have a new optimal solution, provided the ith item is supposed to be included as well. Okay, so the optimal substructure is obvious. That is, if w and if k of w is optimal and it includes vi, then you must have gotten it by taking an optimal solution for w minus wi and then combining it with the ith item. Okay, so once you have this structure, it's quite easy to come up with a dynamic programming algorithm, which basically says, I'm going to take the value of, I'm going to see if I want to pick I or not, and if I pick I, then my cost is going to be the best cost. This should be a capital W, right? So, no, I'm sorry. This is lowercase. Right? Okay. Yeah, I guess I should have used a better notation than to use W to refer to an array and also to refer to the index variable. But as long as you realize that there's being used twice, you can understand. So for ith item, the weight is given by W of I, but we are also using the W for looping through here. So what we are saying is that so we are going to compute essentially in this order, right? So something like we will do K1. Something like that. Okay, so we're going to compute. It may not go exactly in this order because of because the VI's may not be all increasing by. The WI's may not be increasing by 1, so therefore, there may be no K of 2, maybe only K of 3. But the idea is that you start from, essentially K of 0, right, which is really when you have when you cannot carry anything, and then you build up like this. Okay, so the way, so the dependence that larger knapsacks, solutions for optimal solutions for larger knapsacks will depend upon optimal solutions for smaller knapsacks is quite obvious, right? So then what we are going to do is we are going to pick, right? Just like in the increasing sequence case, we are going to take some, and then we are going to see, okay, I can get to this, by going to this item or that item or the third entry here, and then I'm going to pick the maximum, right? Because I want to maximize the value. Okay. So maximize the value across what? I'm going to try each of the items I, right? Because I have items 1 through n, right? I'm going to say at this point I pick item I. Okay. If I picked item I, then if my total budget is W, then what is left for items other than I is W minus WI. Right? So I'm going to go look up my optimal solution for W minus WI. Okay, and then I'm going to add the value of the I item. Okay, so when you do that, you get this solution that so you have this loop here, right? Internal inside loop, which goes through I equal to 1 to n, and then you pick the maximum across all of those i's, right? So when you do that, then you updated K of W for the next value of W, and then you go to W, you set W for W plus 1 and keep going, right? So that way you go from K0, 1, K3, right? All of this, right? So so again, this is without, this algorithm allows repetitions, which simplifies the structure a little bit, right? You don't have to remember at each iteration what items have I chosen already, because if you have a 0-1 knapsack, then you will have to keep track of the items that you've already picked, because those are no longer available. So for instance, if this quantity already includes the ith element, in the case of 0-1 knapsack, you no longer have I as a choice. Okay, so that's something that needs to be kept track of. We'll see that in the next slide, how that algorithm becomes a bit more, involved. But this one is, it's a very simple structure. You have a doubly nested loop. The inner loop goes through n, the outer loop goes through W. So obviously, its complexity is NW, right? So it is filling out the array left to right, or the way we have drawn it here, bottom to top. Okay, and if you construct the DAG, explicitly you'll see that we are looking for the longest path, where the longest means, you are giving the edges a weight corresponding to the value, right? So you want to maximize the value. That means if you add up the length, the values along the path, right? You want to maximize that. Okay, so that's why this is actually constructing the longest path. Okay. Now that, for those of you who think quickly, that should tell you give you another explanation why this is an NP-complete problem, right? So what is the complex? How difficult? So we have looked at some algorithms for computing shortest paths in graphs, right? The shortest paths. The algorithm, the Dijkstra algorithm we looked at is pretty efficient, right? So what about the cost of constructing longest paths in graphs? What kind of algorithms do we have? Can you tell me what could be the complexity of an algorithm that computes the longest path? Right? So because the longest path is, if you have a Hamiltonian path in your graph, well, that would be the longest path, and therefore, since we know that Hamiltonian path problem is NP-complete, so the longest path problem should be very difficult to solve. And not surprisingly, the algorithm we have for computing the longest path in this graph is actually exponential, right? Because if you think about the size of this graph, it's got a size which is not this graph, okay? But if you look at the original problem size, that's actually quite small. Okay, so for 0-1 knapsack, we just have to be a little bit more clever. So what we are going to do is, instead of just keeping a one-dimensional array where the only parameter before was the weight, right? Now we are going to also keep track of the items we have included, and what we're going to do is we're going to say the second subscript is going to keep track of the largest numbered item that we have picked. Okay, so k of u comma j means, okay, I have a weight. I can load my knapsack up to the weight of u, and I am allowed to pick only items 1 through j. Okay, so that's what this means. And then give me the optimal solution under those constraints. Right, my knapsack can hold only the weight of u, and it can hold only items 1 through j. Okay, under those constraints, give me the best value that is achievable, and then by having j go from 0 to n, right? Then you can compute when this number goes to n, that means you no longer have any constraint because all of the n items can be picked. Okay, so that way when you fill this array, not only in terms of increasing weight, but also increasing index. When you finish filling out that array, then you have solved the problem. Okay, so the algorithm itself is on the next page. So you initialize. It says that, okay, I cannot include any items, right? If the largest item I can include is 0, which means I cannot include any item. Therefore, the value I can get is 0. Similarly, this one says my weight budget is 0. Well, if I have a weight budget of 0, obviously I cannot carry anything, and therefore the value I can achieve in both cases is going to be 0, and that's how I initialize these arrays. And then I have a loop where j goes through 1 to n, and u goes to 1 to w. Okay, and then you can see that in this case, right, we no longer have within this 1 to w loop, j is already fixed, right? So inside loop, the body takes only constant time. Okay, so the cost of this algorithm is still nw because there is an outer loop that takes n, that executes n times, inner loop executes w time, and each of the inner loop body execution does not have any iteration, so it's going to be a constant time. So you have another O of NW algorithm. It's just that it's the way you keep track of dependencies, it's a bit more involved because you need to remember what items have already been used. Right? So once again, in all of these dynamic programming algorithms, you just basically all you're doing is trying to figure out what is the dependency structure, right? And then how can I construct optimal solutions to bigger problems in terms of optimal solutions to smaller problems, and look at the dependencies, sort them in some in the topological order, and then you compute the solutions bottom up in that topological sort, and then you get the optimal solution by in a systematic way, right? And the thing about, again, remember that in greedy algorithms, we weren't being systematic in terms of how we chose, how we looked at the problem, so we had to do an extra proof indicating how the final solution was optimal. In case of dynamic programming, it's a systematic technique that searches through the possible, all possible solutions in a sense, right? Of course, if you simply enumerated and looked at all possible solutions, well, then that wouldn't be an efficient algorithm. So you use the structure of the problem to say, well, I don't have to look at every possible answer, but I need to look at only a subset of the possible answers. But this subset, if I search through this subspace, then I can get the optimal solution, and then you do this computation in a bottom-up way, and then that's how you get your solution. Okay, the very last technique, or very last problem that we are going to look at to illustrate dynamic programming is matrix multiplication. Okay, so here is an example where you are given 4 matrices to multiply. Right now, obviously, this 4 matrices you can parenthesize them in different ways, and here are 3 different ways of parenthesizing, right? So you first multiply B and C, then take that and multiply that by D, and finally you multiply by A, right? So if you look at the number of operations involved, well, that's 120,000 operations. Okay, so how do you figure this out? Well, B times C. Okay, B is 20 rows and 10 columns, right? So you're going to take one element here and multiply by one element here, right? So that's going to be 20 times 1, right? So there's going to be just one multiplication involved here when you multiply B and C. So you'll have, this is the cost of multiplying B divided by B multiplied by C. Okay? Now, if you look at it, then you can easily see that the way to compute the total number of operations involved is simply to multiply these 3 numbers, right? The number of rows in the first matrix times the number of columns in the first matrix times the number of columns in the second matrix. Okay? These numbers will, of course, have to match in order for the multiplication to be defined, right? So you multiply these 3, that tells you how many multiplications you have to perform. And so B times C multiplication takes 20 times 1 times 10, 200, right? Now, when you are done with this, the resulting matrix has the size 20 times 10. Okay? So again, that's something that's in matrix multiplication. When you do this, the number of rows of the resulting matrix will be the number of rows in the first matrix, and the number of columns in the resulting matrix will be the number of columns in the second matrix. Right? So you have you are left with a matrix of size 20 by 10. Now 20 by 10 matrix has to be multiplied by a 10 by 100 matrix. So that gives you 20 times 10 times 100 cost. Okay, and this is where things quickly add up. So this is 20,000 operations, and finally you are left with a matrix which is 20 rows by 100 columns, right? So when you have finished multiplying all these three, you have a matrix that is 20 rows by 100 columns. And then you multiply that by this, so you have 50 times 20 times 100, right? 50 times 20 times 100, well, that is, what is that? That's 100,000 operations, right? So the total number of operations when you parameterize this way comes out to be 120,000. But if you parameterize in this way, then you can work through the details. So you can see that this is 50 times 20 times 1, okay? And then we're going to do C times D, which is 1 times 10 times 100. So that's here. And now you're left with 1 matrix. Okay. So now you're left with one matrix that is 50 times 10. I'm sorry, 50 times 1, and another one which is 10 times
10. 10 times?
No, 1 times 100. Yeah, right. So these two are
Yeah,
1 by 100, and this is 50 by 1, right? So you have, so the resulting operation is going to be 50 times 1 times 100, which is quite small. So here you get away with doing a very small number of multiplications. So it might seem unintuitive that, well, okay, you might think, okay, matrix multiplication is associative, I can just do it in any order. But you can see that depending on the order in which you do it, it can make a lot of difference in terms of how expensive the overall cost is. And so it makes sense to say, okay, what is the optimal way to perform this matrix multiplication? Okay, so that is another problem which can be formulated as a dynamic programming problem. Okay, and we can think about it, recursively. So you can say, well, what is the outermost multiplication we are going to perform? Okay, then let's say that is going to be, you're going to split between j and j plus 1. That means, you're first going to compute the product of m1 through mj, and somehow you're going to compute mj plus 1 through mn, and finally you're going to come, this will result in one matrix, this will result in another matrix, and you're going to multiply the two. Right? So this is what you're going to do. So now the optimal substructure is that if this is the top level multiplication, and let's say you do that, now to get an overall optimal solution, then you need to compute this subproduct optimally and this subproduct optimally, right? Because otherwise, well, if you say, otherwise you can use the usual switching argument to say, well, if somehow you could take a non-optimal solution and use it to achieve an optimal solution, well, then one of them is not optimal. Your claim that both of them are optimal is incorrect. Okay, so this is a contradiction that I can arrive at by switching one out for the other. So that is the optimal substructure. So what we are going to do is we are going to compute these optimal ways to do the product in a bottom-up way. Okay. So now what we are going to do is we are going to remember the cost of computing m1 through mj using it costs a two-dimensional array. Okay. In particular, C, K, L denotes the most efficient way of computing the subproduct starting from mk through ml. Okay. So essentially, think of this whole thing as if it's a string. Okay, m1, m2, m3 up to mn, and then your subproduct is going to be like a substring, right? Because again, you can't matrix multiplication is not commutative, so you can't rearrange the order, right? Which means that the sub products that you pick, they still have to occur in the same order as the original. Okay, the matrix, and therefore the sub problems that you're considering are like a substring of the multiplication. Okay, so that's why your cost function C is going to be a two-dimensional array because what are the number of, for each possible k and each possible L, you have to keep track of the optimal way of doing the product, and so essentially it becomes a two-dimensional array. Okay? So now we can give the algorithm. Okay? So C of I comma I, so we initialize, right, is 0, right? Because well, C of I comma I is performing a product of matrix I and nothing else, right? So there's no work to be done. Therefore, C of I comma I equals 0. Okay. So now what we are going to do is we are going to do this two-level loop. The outer loop basically says what is the length of the substring for which I'm going to compute the cost. Okay. So I'm going to start by setting this length to be 1. Okay, and then I'll go to the length equal to 2, 3, and so on. Okay. Now, what is the exact substring that I'm going to consider? The substring that I'm going to consider is going to be something that runs from K, position K, to a position L, where L is obtained by K plus S. Remember, S is the length of the substring, so the end of the string is given by adding the length of the string to the beginning of the string. Right? So K is the index position where the sub product starts, and you want to go for S more things, then the ending place is going to be K plus S. Okay. So now C of K comma L is going to be right. So let's make sure that we understand what these numbers mean. Okay. So matrix Mi, right, capital Mi is going to have size Mi minus 1 rows by Mi columns. Okay. Remember that again, because they have to be, you should be able to multiply matrix Mi should be multiplied by Mi plus 1, right? So this means if this has some if this is an A by B matrix, then this must be B by C matrix, right? So which means that these two should always be the same, and that's why we are able to say Mi has the size, this you would call as Mi minus 1, and this you will call as Mi, and this is going to be Mi, and this is going to be Mi plus 1. Okay? So this is the notation we are going to use to represent the sizes of the matrix. And so now we can take the cost of multiplying Mi and Mi. So now the cost of multiplying two matrices we know is obtained by taking a product of this, and that, right? So that's all we need to do, and that is what we're doing because. So remember that what we are doing here is we are trying to find out the cost of performing the last multiplication here, right? So C of K comma L, right, is so what we are trying to do here in that loop is so notice that there is another loop here, right? So what we are trying to do is we are trying to vary this I as it goes from K through L. Okay? So what we are trying to do there is we are saying that the optimal way to compute Ck comma L involves computing. So we are trying to compute the optimal solution for performing So remember that C of k comma L tells you the cost of the optimal way to perform the multiplication or compute the subproduct of matrices mk through ml. Okay? So that's what I written here, right? So okay, so what is the optimal way to perform this subproduct? That's what this is telling you. Okay. So the way we are going to do that is we are going to consider every possible position where this could be further subdivided, right? So we're going to take some fraction like this and another fraction like this, right? Where that's your I. So you're going to take the product up to subproduct from k through I, and then you're going to compute the subproduct I plus 1 through L, right? And since you are going in increasing order of these lengths, so the k through I, right? So this length and this length are both less than that length, which means that by the time you are coming to compute the optimal way to do the subproduct k through L, you would have already computed the optimal way to do the subproduct for mk through mk plus I and mk plus I plus 1 through mx, right? So both of these you would have already computed. So you add that, and then in addition, you have to worry about the cost of performing this particular step, right? That this step, you have a matrix, okay, which let's call this as let's call this matrix A, and let's call this matrix B, right? Because A combines mk through mk plus I, right? Its size is going to be given by the number of rows in mk. Okay, so number of rows in mk is mk minus 1, right? That is the convention, right? So mi has lowercase mi minus 1 rows, which means that this product is going to have number of rows equals mk minus 1. Okay, and then B is the number of columns is going to be the number of columns in this matrix, right? The last matrix here, which is going to be ML, right? So for that matrix, there's the number of columns into ML, and then we're going to pick up the size of the first matrix here, which is M k plus I plus 1, right? So this matrix, the number of rows is M of, so the number of rows in that is going to be right? Did I get that right? No, mi, okay. So I guess, yeah, okay. So this is not I plus k plus 1, this is just I plus 1, right? So this is I is not beginning, so this is the position I was getting confused and thinking that I was relative to k, but I is not relative to k. I is starts from k plus 1, k plus 2, it goes that way. Okay. So now what we have done is basically we know we have already computed in previous iterations the best way to the lowest cost way to multiply mk through I minus 1, and then we also have the best way to multiply mi plus 1 through ml. And now we are going to simply compute the total cost, which is you compute the subproduct, and then you have two matrices to multiply. And what is the cost of that multiplication? And that is going to be this, based on the sizes of this, the matrix is something from this subproduct, and the matrix is something from this subproduct. From that you can compute the cost. And you put that all together, then you get this equation. Right? So this is the optimal way to do the first subproduct, optimal way to do the second subproduct, and then to do the outermost multiplication here. Okay? So now you are going to try breaking up the substring k through L at every position I, and across all of those compute which is the best. Right? So again, this is a systematic search through all possible solutions, and then of course it's no surprise that at the end you should have the optimal solution for computing the matrix. Okay, so finally you might ask, okay, what is the cost? Are we spending so much time computing the optimal way to do this product that in fact we didn't really save a whole lot? But that's not the case. So the cost of performing this this algorithm is order of n cubed, right? And n is not your input size here. Remember, n is your input size is the sum of the sizes of these matrices together, right? And each matrix could have arbitrary size that has nothing to do with n, right? You could have n equal to 2, and your matrices could be a million by million, right? So doesn't so this is not comparable to the cost of the performing the multiplication. But what that tells you is that if all your matrices are small, right? Let's say you have 2 by 2 matrices, and you have 100 of them, right? Then you'll be better off just performing the multiplication instead of thinking about what is the optimal way, because the optimal way has 100 cube operations, whereas simply performing 100 2 by 2 multiplications is very, very cheap. Okay, so that's so the very last point I'm going to talk about is whether you need to do dynamic programming in a non-recursive way, or if it's okay to think about it in a recursive fashion. So you can see that in every algorithm we have written down so far, there was some kind of an ordering, right? So that's why we started describing, when we started this unit, we talked about topological sorting, because we said that all dynamic programming algorithms, there is a dependence between the optimal solutions for different subproblems, but there is no cycle in this, and there is some order, and you can compute that in the right order, and therefore all of the solutions all of the algorithms we've written so far are non-recursive, and they compute somehow. They sort of say, okay, let me compute the optimal solution for smaller subproblems, and gradually from that I'll compute the optimal solution for bigger subproblems, and so on. Right? So this is what we have done, but sometimes it's not very convenient to try to explicitly spell out this optimal substructure and actually have to do this in a non-iterative fashion. Okay, so instead you could potentially do this recursively by simply remembering values. Okay, so the easiest way to understand the point I'm making is to think about Fibonacci, right? So we know that right? So you have this iterative formulation of this, which says f of, if you compute f of 1, and then f of 2, and f of 3, and f of 4, and f of 5, and if you do it in that order, then you have a linear time algorithm, assuming, again, you don't worry about the cost of multiplication and so on. But you could also think of this, Fibonacci we understand in its recursive form, right? This is how we understand Fibonacci. If somebody gave you the Fibonacci sequence, unless you have worked with Fibonacci series for a while, you probably won't recognize it, right? This looks like some sequence of numbers. But if somebody tells you this recursive equation, then you'll immediately say, oh, this is Fibonacci, right? So the question is, when you have some problems which are more naturally formulated in a recursive way, can you gain the benefits of dynamic programming without having to, unwind this dependency in such a way that at the end, you can apply dynamic programming? So the answer is that you can keep a recursive formulation. The only thing that you need to do really is to remember the solutions in your computer, right? And if you do that, well, you get the same benefits of dynamic programming. So for instance, in the case of Fibonacci, well, you start with f of, let's say, 10. Well, you know that requires f of 9 and f of 8, right? And then f of 9 again requires f of 8 and f of 7, right? And the reason why this naive algorithm becomes exponential is because f of 8, just like f of 8 is appearing twice, there are many sub-computations that will be repeated again and again. But if you have, if you can remember these sub-computations and don't recompute those, then you can do this recursive formulation and still be able to do this very quickly, right? Because so for instance, you start, let's say, f of 5, right? Right? So what you're going to do is you're going to compute f2 once. So you remember that. So all these, you will never expand. Any of this you won't have to expand, because by the time you are coming up the recursion tree, right? So f5 will call f4, f4 will call f3, f3 will call f2. By the time you unwind and come here, right, or come here and ask for f of 3 again, f of 3 has already been computed, right? So you can just pick up that solution if you stored it somewhere instead of having to recompute it. And once you avoid recomputation, then you can see that essentially evaluation will only proceed on this left spine of the tree, right? The rest of the tree will never be even be constructed. Therefore, you will have a linear time solution, even though you are not really explicitly making it an iterative algorithm. And so this technique is called memoization. That is, you compute a function, right, and you remember it, so that in case the same function, you need to recompute it in the future, you can just pick up the old value. Okay. So obviously, if you think about programming, you have to be careful, because when you write programs, many functions that you write in your typical language, return different values each time you call them, right? So memoing is something that you cannot blindly apply when you program. You have to make sure that when you apply memoing, then you are really talking about pure functions, right? Pure functions meaning that they behave like mathematical functions, which means that if the arguments are same, the result is always going to be the same no matter how many times you call them. Right? In those cases, you can remember and reuse results from previous time, and once you do that, then you get a lot of the benefits of dynamic programming. Right? So you get the benefits of dynamic programming without having to actually unroll the computation in the way that you have done so far. Okay? Now, this does not mean that somehow everything we learned about dynamic programming is not useful, right? It's just about having to decide in advance what is the order in which you are going to perform the computations, right? So it's not about understanding, so the equations themselves don't change, right? So you're not changing the equation that defines the function. All you're saying is that I don't have to go ahead of time, figure out what the dependency structure is and perform the computation bottom up. Instead, I can start at the top and go down, right? And still I'll get the right answer. But the dependencies have to be set up right. So all the equations that you set up, right, they will not change. The only thing is that you don't have to explicitly do this sort of. So for instance, look at this equation, right? So you have to explicitly set it up so that you are working with subsequences of larger and larger lengths, right? But if you simply look at this equation and do this recursively, right, then automatically, right, when you go for the optimal solution to k comma l, you are going to break it at some I, and the subproblems are automatically going to be smaller, right? You don't have to sort of decide in advance, I have to, create this array in this way. Okay? So you will find that if you go back to most of the algorithms that we discussed in dynamic programming, there is a certain level of simplicity that comes from thinking about it in a memorized fashion, in that you don't really have to draw this dependency graph and evaluate it bottom up in the dependency graph. Okay? So, but historically, right, so just due to the way algorithms were developed, so you can imagine that when algorithms were developed long ago, people thought recursion was inefficient. They always knew that recursion was elegant. It makes the problem specification simple, but it wasn't considered efficient to write recursive functions. So you can understand that there is a preference to iterative solutions, and that's why dynamic programming is always described in terms of this kind of iteration rather than thinking about it in terms of memoing. But what you will find is that if in your work at some point you end up writing a dynamic programming algorithm and it happens to be very complex, if it happens to involve a complex computation, you will find that thinking about it in terms of memoing makes it a lot simpler to implement than to do this in a sort of strictly bottom-up way that you will go ahead of time. Okay, so there are more examples that try to show how the memoing version is simpler. I'm not going to go through this because I think the Fibonacci is actually a much simpler way to understand how the recursive version is simpler than non-recursive version. Okay? So instead we are going to go on to the next topic, which is actually we are going to talk about shortest path problems. So many of these shortest path problems aren't historically thought of as dynamic programming problems, and they are not dynamic programming problems because very often they involve cyclic dependencies. Okay? So what we are going to do is instead we are going to think about the problem in terms of equations and equation solving. Okay? So if you notice, in all of the dynamic programming problems that we have done so far, what we did was we set up some equation that says the optimal cost of this larger subproblem is somehow, this is computed as a function involving the cost of subproblems. Right? So there is always this equation that says the cost of the optimal cost of bigger problem and in terms of optimal cost of the subproblems. So this type of equation is really, setting up this equation is really the crux of dynamic programming. And we can see this type of equation set up as being able to do something much more. Okay, so essentially in dynamic programming, what you do is that you form that equation and then you set up a schedule for solving this set of equations in a bottom-up way, so that there are no cycles. So you can start at the leaf and then compute the solutions of the higher nodes. Okay, and that's possible because, again, as we said, the dependencies need to form a DAG. So now what happens if there are problems where the dependency is not a DAG? Okay, it looks like, at least on the surface, it looks like the dependency is have a cycle. Okay, so cyclic equations, right, aren't anything unfamiliar to us, right? We have seen simultaneous equations in the past, right? It's something that you learned from your middle school or maybe even before, right? So you have simultaneous equations where x is defined in terms of y and y is defined in terms of x, right? But you know how to solve that, right? There is a recursive dependency or a cyclic dependency, and you know how to solve that, right? So the way that you solve them usually is to do some kind of elimination that basically expresses each variable in terms of other variables in a way that there isn't a cycle. Okay, but there are also solutions that look at equations as they are, and they use iterative techniques to compute solutions. Right? So let's look at what some of those are. Right? So the term fixed point, this is something that you often hear in a programming language course rather than an algorithm course. Right? The terminology is not commonly used in algorithm course. But a fixed point just means a solution to an equation. Right? And why is it called a fixed point? Because if you have a solution to an equation, then if you substitute the values of, let's say you have okay, so let's say what is the solution? Well, maybe this is not. Let me think of the solution and then write the answer, right? Okay, so I guess there is a solution to this, which is x equal to 2, y equal to 3, right? Okay, so the point is that if I substitute the values, right, then the equation would. So now let me write it down in a. Let's take that equation, right? That's both x and y on the right hand side, right? So we substitute x on the right hand side. So I get 3 times 3 minus 2. That's equal to 2, right? So what I'm trying to illustrate is that if I try to compute a new value for x by substituting existing values that I have computed for x and y, then I get the same thing back, right? So the definition of a solution is that if you plug in the solution, the computed solution on the right hand side, you will get the right value for the left hand side. Okay? So that is the definition of a solution, and that's why it's called a fixed point, because once you find this and you keep substituting, then you will get the same value back. So let's think about it. I guess I have better examples here. Okay. So let's think of y equal to y squared minus 12. Right? It's a quadratic equation. Of course, you know how to solve a quadratic equation. But let's say we are going to use use this to illustrate the fixed point. So if you substitute the value on the right hand side, okay, that is already a solution, then you'll get the same thing, right? But if you substitute something else, okay, let's say 5, right? Then y will be 25 minus 12, minus 12, which is 30, right? So you don't get the what you substituted in, right? So then that is not a fixed point. On the other hand, if you substitute 4, then you get 16 minus 12, well, you get 4, which was the original value of y that we substituted, right? So that is a fixed point. Okay, so now, so a fixed point is a solution to the equation, and I guess, it can be applied to regardless of the number of variables that are involved, right? So how many of you remember iterative techniques to solve simultaneous equations? How many of you have done it in your group? No? Only one person has heard of iterative solutions to simultaneous equations? What about iterative solutions to find roots of polynomials? No? How do you compute roots of polynomials? There are various techniques, but the basic idea involves guessing a solution, and then you substitute it, and then you'll get some result, and then you have some way of adjusting and picking a new solution based on the result of the substitution. Okay? There are various techniques that use things like derivatives to tell you what should be your next guess, right? And so these kinds of iterative techniques, we use them in various places, and the question is whether those types of iterative techniques are, how do they relate to the kind of equations and equation solving that we see in dynamic programming and shortest path algorithms. Okay, so that's so when you use these kind of iterative techniques, one of the issues is convergence. Right? So you might, if you picked your initial guess right, then your successive solutions will get closer and closer to the correct solution. Okay, and if you made a wrong guess, it is possible that your solutions won't converge, but instead you go farther and farther from the real solution. Okay? So this is for real value variables. There are various conditions depending on the nature of the problem that you're solving that tells you when the solution would converge and when it doesn't. But in algorithms, we typically work with discrete domains. Okay, so you have, when you think about data distance, well, there are strings are discrete, and the way we set up, the problem in terms of data distance between prefixes of two strings, right? That's how we set it up. Everything is discrete. So in discrete domains, we have a different way of thinking about convergence, and that is based on two properties called monotonicity and well-foundedness, which basically says, you can start so monotonicity basically says that you have an equation, right? And so a function is monotonic if right? So if you give larger inputs, then the output can only get larger, right? So it may stay the same, but it cannot shrink, right? That is monotonicity. So if you go, so when you have a monotonic function, and if all your equations involve monotonic functions, what that means is that you can start from some minimum point in your discrete domain, and you substitute that value into the equation, and the result you get will be a point higher in the domain. Now, if your second approximation is here, and you substitute that, then you can only keep going up, right? If all your equations are monotonic, then what you can say is that your iterative technique will keep going up. And if you have this notion of a well-founded order, which basically says you cannot keep going up forever, so those two conditions combined together will allow these kinds of iterative techniques to converge in discrete domains. Because in discrete domains, everything is finite. If there isn't a way to go up infinitely, right? So in a well-founded order, that tells you that you cannot go up infinitely, and therefore if you can go up only a finite number of times, and you can never go down, well, that somehow means that you're going to reach your solution. Okay? So this is sort of the general background that you don't have to really know, but in case you want to understand why these things terminate, then you can understand. Okay, so let's skip ahead and so what we're going to do is we are going to look at shortest path problems as equations, and we are going to understand various shortest path problems as different techniques to iteratively solve these recursive equations. Okay? So the idea is that by looking at all of them in this uniform framework, it's easier for you to learn more algorithms in a shorter period of time, and hopefully also the common structure will help, will make it possible for you to remember these different algorithms. Okay? So the single source shortest path problem can be written in terms of this equation: distance from a single source, right? So distance of vertex v from a single source, right, which is sort of not mentioned in the equation. So we have, in the Dijkstra case, there was this algorithm, this source S. So we are computing the shortest path from the source S to a vertex v, and that should satisfy this property that so you have S, right? And you have V, right? Now, so there is a path from S to V, okay? So let's take the vertex U, that is the last vertex before you reach V, right? So then the optimal cost of the path from S to V is going to be the optimal cost of path from S to U, followed by the length of U to V, right? For some predecessor of V, right? So what we are saying here is that you pick the predecessor of V, which has the lowest cost to S, right? So this is what this equation says. You pick, so because we are talking about the edge U comma V, so U is the predecessor of V, and what we are saying is that pick that predecessor of U, V, such that this combination, right, that is the cost of getting to U followed by the cost of traversing that edge from U to V, that cost is minimized, right? So this is the equation that exposes the optimal substructure in the problem. right? So the path that goes all the way from S to V should involve an optimal path from S to some predecessor of V. Okay, so we have that equation. Similarly, if you want all pairs shortest path problems, then again you can write that in a very similar way. In all pairs, then you have two vertices to consider, right? You are trying to find out the lowest cost path from vertex U to vertex V. Okay, so that might, so you have vertex U, vertex V, and the optimal path will go through some W in between, right? And so the path from U to W and W to V should both be optimal. Right? They should be the lowest cost path, right? Otherwise, there would be some other way to get from U to V that's short, right? So the shortest path from U to V for the vertices that are on this path, you should already have a shortest path to those vertices, right? So this says D of U comma IV, you're going to pick some intermediate vertex W such that the sum of the cost from U to W and sum of the cost from
Either we already have seen the path or
right. So this is this equation says to go from U to V, it is the solution that you already computed, or you compute a new solution that involves going through some intermediate vertex W, and then you combine the cost, right? So of course you're going to pick the minimum across all of them, so you should get the absolutely lowest value. This formulation is looking at it through so this formulation is picking an arbitrary intermediate vertex W. This formulation is picking a W that is a predecessor of V, right? So just like in the case of single source problem, right? So here we were picking iterating only through the predecessor of V. Here we are iterating through arbitrary W. In all cases, these equations themselves are relatively simple to understand and simple to convince ourselves that they are correct, right? It's not the same thing as saying that, okay, from this equation I can compute, I can come up with an efficient algorithm. That we haven't done, but to understand the equations themselves it's pretty easy to do. Okay, so what we're going to do, I'm going to stop a little bit early today because I have to leave for a train. So essentially what we are going to do is I'm going to stop here, and we will come back and discuss all of these shortest path algorithms as solving these equations. Okay, and there are various ways to optimize this solving process, and each of those ways yield a different shortest path algorithm. Okay, we will be looking at that in the next lecture. Okay, so the solution for the next homework, for the last homework, has been posted. I just posted it a few minutes before the class. So we will have our regular class on Thursday, and your exam is on Monday, right? So any questions? So what did I say? I said something. So I would not expect you to solve new dynamic programming problems, but I would expect you to recognize the dynamic programming problems that you've already seen in class. How about that? Right? So I'm going to expect you to know that edit distance algorithm has a certain complexity, right? The knapsack algorithm has a certain complexity. I would expect you to know that. but I won't expect you to, I won't give you a variant of edit distance algorithm and say, solve this problem. No. So you don't really have to understand and prepare in detail what this is, but just be familiar with different algorithms we have looked at and what their complexities are. Okay, and then understand what the problem is. Okay, you don't have to understand how to solve them. Solution is not that important. Understand what the problem is, and then understand what is its complexity, and that might be something that I might, you know. So questions may relate to that, but not a detailed understanding of the algorithm.